Okay, so here we go. Can you see the slides? Okay, so there's been a lot of talk about humanoids lately, right? I mean, AI and humanoids are dominating and the conversations. And so I would say that humanoid robots have been walking, talking, and falling for decades. But what's changing now isn't just how the robots move. What's changing now is how the robots think, how they perceive, and how they interact. However, the dream of building machines in our own image is still far off. Or maybe it's a little bit closer. Our dream of bringing machines in our own image that are intelligent and obedient really goes back to antiquity. And with the advancements in humanoid platforms and robot control, we seem to be coming closer, but it also seems to be more complicated than ever. So let me try to unpack this for you a bit. Okay, so earlier this year in China, a group of humanoid robots attempted a half marathon. That was pretty cool, right? But most of them didn't make it to the finish line. However, a few did, and that's really a great achievement. And so what we have seen at the marathon in China was less a display of speed and more a testament of persistence. And just how hard real-world mobility is for machines designed to move like us in environments like our environments. Now, watching those robots struggle and adapt along the course should remind us of something very fundamental, that building a humanoid isn't just about legs and motors. It's also about the head. It's also about coordination, perception, and decision-making in real time. And so, in other words, a humanoid robot is more than just a body. A humanoid robot is a body plus a brain. The body is the hardware. The brain is the software, the algorithms that gets the robot to reason, to learn. And so, true progress can only come when these two evolve together. And so what gives a robot its real capabilities isn't just the hardware component. It's the connection between body, perception, and action. And intelligence emerges not just from processing data, but also from using the body to sense, to move, to respond in this complicated world. And when perception and action are integrated, robots begin to behave. Now, recently, we have begun to think about whether adding language to that loop makes sense. And when we bring language into this robot control loop, something even more powerful happens. Because language becomes a bridge between abstract reasoning and embodied experience. It allows the robots not just to act, but also to explain, to learn from humans, and to align their behaviors with our goals. And so it really turns hardware platforms embodied intelligence into partners, into physical partners. So as these capabilities, embodiment, perception, action, and now language begin to converge, we are seeing a surge of interest, not just in research labs, but also in companies, in business. And the idea of a general-purpose humanoid is beginning to move from science fiction to startups, to pitch decks, and to a growing number of companies that are racing to define what a commercially viable humanoid is. And these are some of the companies and their robots. And what's interesting is also to see where the action is. So this is where the companies are. And you see that about half the companies are in the US, half the companies are in Asia, and then we also have engineered arts in the UK. One of these companies is Figure AI. Figure AI is aiming to build a robot that will be a true partner to people in the home. And the Figure AI is an American company that has benefited of massive funding and is really pushing all of its resources, financial and intellectual, to building advanced intelligence, to building machines that can interact with the world, to really building physical applications that we imagine or we have seen humanoid robots execute in movies. The potential for market uptick is huge, and so this is how the projection of the humanoid robot market side looks like. By 2030, we're looking at nearly 40 billion. This is a lot of money. But the thing is, we have a ways to go in order to harvest those fruits. And this really requires that we put effort in building technological advancements in multiple areas. First of all, in advanced AI and reasoning. Secondly, in manipulation and interaction with the world. This is what I call by enhanced dexterity. Thirdly, in sensor integration, because we need to enhance the perception aspects of these machines. And finally, in power efficiency. I can run a whole day on a bar of chocolate. Now, what can a robot do with that much energy? Nothing. So we really need to make progress in that space. We have both challenges and opportunities in this space. So we have technical challenges related to reasoning, related to battery limitations, related to cost of production. We also have market opportunities because humanoid robots could really do so much more than what other types of robots, specialized robots, do. And so as I think about the potential impact of humanoid robotics in business, I can imagine this pyramid where time goes up. And maybe the pyramid should be inverted from the point of view of the size of the pie. But in the near term, I hope we can see economic impact through new jobs and through new industries that are emerging as a result of humanoids. And then humanoids could really make impact in specific verticals, for instance, in healthcare. Eventually, I see humanoid robots making a difference in manufacturing and finally in everyday integration. And so everyday integration is much harder than, for instance, manufacturing, because manufacturing is a much more well-specified environment, much simpler environment than the messiness of the human environments. I mean, even this room would be such a nightmare for a robot to navigate right now. So this connection between body perception and action can lead to extraordinary capabilities. And I'm sure you have all seen the extraordinary dances of the Boston Dynamics robots, Atlas and Scott. My favorite is when they dance with Mick Jagger. However, you may not know how those dances were created. And so I just wanted to quote from an article. A year and a half of choreography, simulation, programming, upgrades. So a year and a half of programming every single movement of those robots, capped by 2 days of filming to produce a video that ran less than 3 minutes. So, so the thing is, these robots can do extraordinary things, but it's not so easy to get to those outcomes. Now, you have probably already seen some robots, or no, the Living Lab. You're going to see some robots later today in our research space. So here's one of our robots, and it's learning to walk. It's doing pretty well. It's doing pretty well. Like you can see, it can be interactive. Like it can even respond to the human. But it can also do this. Check this out. So now it's trying to take a step, and right. So controlling these complex mechanisms is really hard. That's the moral of this of these slides. Now, but there is also very much optimism. So, for instance, Tesla introduced Optimus. I love the name Optimus. It's so optimistic. So Tesla introduced Optimus in 2022, and the robot is supposedly in production now. And by 2030, it is expected that about 1 million units will be in factories, working side by side with people. And so So this is really the dream of Elon Musk. Now, I think Elon Musk is a great visionary, and I wouldn't bet against his visions. But Elon Musk often gets the timing wrong. So, for instance, he also said that by 2021, we will be falling asleep at the wheel. And now it's 2025, and we're still not falling asleep at the wheel. If you have a Tesla, please don't fall asleep at the wheel. So essentially what we learn is that humanoids are complex mechanisms that are hard to control. Now, when language gets added to the mechanism, we can really imagine wonderful human-machine interactions. And I want to share with you an interaction I had with a humanoid at the conference I attended recently. So let's try to listen. Hi, what is your name?
I'm Neo.
And what can you do, Neo?
I help out humans in their homes.
I didn't understand that. Can you repeat?
I help out humans in their homes.
Oh, you help humans. Can you water that plant over there?
Yeah.
I was asking why put it in a sweater rather than using some sort of rubbery
That's pretty good.
exterior that gives off heat more effectively.
Oh yeah, well we've been doing multiple testing, and this is kind of the compartment that so far as the easiest to pull on and take off. It has the electric fabric that we use.
That's very good, Neo.
I'm sure there are other
Can you water my friend here?
that we can use as well.
Yeah.
No, I was just kidding. Don't do that. What else can you do? All right. So my friend, by the way, had really expensive shoes, and I could imagine a gallon of water on top of those suede expensive shoes. So it's interesting because even though we have these seemingly really extraordinary capabilities, these machines don't have common sense, and that's because common sense is actually lacking within our current solutions. But that doesn't mean we're never going to get to the point where the solutions are better. And so to me, in order to make humanoids work better, both physically and also from a point of view of reason, we need for AI to be better. And so this is actually what I want to tell you today in the rest of my time. I want to tell you about a new way to think about AI, which I call physical intelligence or physical AI. And physical AI is when we can increase the brain's capabilities of robots by using AI's power to understand digital text, images, and other online information. And so this is synergistic to what you might know as embodied intelligence, which concerns how you use the hardware, how do you use the body in order to get the robot to adapt to its environment in an intelligent way. And so the point today is that in the field of robotics, right now, we have two largely separate fields. We have artificial intelligence and we have robotics. And AI is amazing us with its decision-making and learning, but it's confined inside computers. Now, robots have a physical presence and the ability to execute pre-programmed tasks, but they're mostly not intelligent. And so my objective is to bridge this separation. With physical AI, AI doesn't just reside in our computers, but it walks, rolls, flies, interacts with us in the real world. For instance, imagine a helpful robot at the supermarket. The robot could help you carry something heavy to your car. So in order to make physical AI work, we need to change how AI thinks, how machines are designed, and how they learn. So it is challenging to use today's AI models on safety-critical applications, such as the ones with robots, because these models make mistakes. For example, this AI system for a robot car is very good at detecting individual pedestrians because it saw a lot of models of individual pedestrians, but does not detect reliably groups of pedestrians because they are amorphous in shape. So for physical AI, we need brains that do not make mistakes. For physical AI, we also need AI software that can run on small computers on the body of a machine. For example, our robot fish. And today's AI doesn't fit because it requires server farms. And additionally, today's AI has a very high energy cost, which cannot be covered by onboard batteries. And I would like to explain to you a little bit the energy cost. So today we have extraordinary frontier models like GPT, Claude, and Gemini. These are very large models that have on the order of trillions of parameters. A trillion is something we can't even wrap our head around. And these models are built on two very energy-intensive phases that are called pre-training and fine-tuning. And so the goal of pre-training is to have the model learn the general knowledge embedded in the data. So pre-training kind of memorizes the data that's used to train the model. And these models are trained on between 1 and 15 terabytes of data. And the training results results in learning the weights of a model, so that you can use this model to do next token prediction, and you can generate sentences. And so, for example, after pre-training on many facts, this model can predict correctly in which year the first ISSCC, this the International Chips Conference, was held. So the second phase is called fine-tuning, and this one uses specialized data to adapt the model to be useful for downstream applications. And examples of downstream applications are summarization, filling out tables, things like that. So not generating text, not doing next token prediction. And to do all this training and inference, AI consumes a huge amount of energy. On the left here, you see the US data center energy consumption, which is projected to 2030, and the consumption is in terawatt hours. And on the right, you see the data center share of total US power. And as we scale AI in search for more and more capabilities, these numbers continue to grow. And there are predictions that the numbers could be anywhere between 6.7 and 12% by 2028. So what can we do to reduce the energy cost? Well, one solution is to simplify the model without losing its effectiveness. And one technique is called pruning. And pruning is essentially says we're going to remove unnecessary neurons and connections or parameters from a neural network. And so basically pruning removes the weights that don't matter. And another method called quantization reduces the precision of weights and activations in a model. And by representing numbers with fewer bits, quantization reduces the memory footprint and improves the inference speed. So for example, instead of using a 32-bit floating point number, quantization can use 8-bit integers, and that requires less space. And so it's very interesting, because using these techniques, we can reduce the energy cost of models. By the way, DeepSeek has used these techniques along with some other great engineering to achieve the extraordinary results that they have published in 2025. Now, the energy savings we get with these techniques can support more scaling. And it's actually very interesting, because our most recent results show that as we continue to build larger and larger AI models, we're also beginning to see that this thesis that pure scaling will give us more capability, this thesis no longer holds. We are beginning to see diminishing returns from the point of view of capability. And here's some data that shows you. You see it's moving kind of like an S. So scaling helped us on the sharp edge, but now we're getting to the top of the S. So this raises an important question. Are there new ideas that will not make mistakes, that will result in small models, and that can fit on robot bodies and can lead to better performance over transformer-based AI architectures? And so a lot of people in the community are asking this question. In my lab, we are taking a particular approach, which is inspired by nature. It's inspired by a worm called C. elegans. C. elegans has inspired a lot of the neuroscience literature to date. So we're using C. elegans to answer this question. C. elegans is very interesting because in stark contrast to the billions of neurons in the human brain, this worm lives happily on only 302 neurons. And biologists understand how these neurons work. So here's the idea. Can we use the mass of the worm to understand and build a new class of AI models that are more capable? And for us, these models are liquid networks, which are compact and explainable and capable as compared to today's solutions. Let me explain you why. So this is our self-driving car. And here you see the self-driving car trained using a traditional AI solution, the type found in many applications today. And here you can see the dashboard of how this car makes decisions. In the lower, right corner, you see the map. In the upper left corner, the camera input stream. The big box with the blue and yellow dots is the decision-making engine that tells the car how to steer. This car learned how to steer and accelerate because it looked at many videos of human drivers, how they steer and how they accelerate depending on what the environment looks like. And so in this box, there are like tens of thousands of neurons and 500,000 parameters. And it is impossible to correlate how those neurons fire with what the car does. And furthermore, if you look at the lower left corner, this shows the attention map. This means where in the image the big box, the decision-making engine, looks in order to tell the car how to steer and how to accelerate. And you notice how noisy it is? This solution looks at the context of driving. It looks at the entire image. But that's not how I drive. I bet that's not how you drive. You don't look at the bushes and the trees next to the car when you drive. You look at the road horizon and the side of the road at the horizon. And so, interestingly, when we apply our liquid network solution, this is what the dashboard looks like. So look at the attention map. It's focused on the road horizon and the sides of the road at the horizon, and it's not distracted by the context of the road. And the solution has only 19 neurons, and because the solution is so much smaller, we can actually understand the role of each of these neurons in the decision-making process. And so how did we do this? How is this possible? Well, here's the math. So in most traditional AI solutions, the artificial neuron is an on-off computation, so it puts out a 0 or 1. It takes in some numbers, it adds them up, it applies some basic math, and then it passes along the result, which is 0 or 1. And this becomes very complicated because it's happening over so many computational units, thousands and hundreds of thousands and millions of computational units. Now, liquid networks use fewer neurons, but each neuron does more complex math. They are not simply on-off computations. And so essentially we use differential equations to model the neuron and also the synaptic connections. These differential equations are inspired by the math of the worm, by what biologists said was happening inside the worm. And if you plug the synaptic equation into the neural computation, you get this hairy thing. And so this is the output of the neuron in liquid networks. And this is interesting because if you look at this term and you know a little bit of math, this is the time term for the differential equation. And normally it's constant. In our case, it's liquid because it depends on x of t. This is where the name comes from. The other thing that's interesting is that this differential equation has a closed form approximation with an upper bound. So this means that we don't need numerical integrators to compute the result. And this means, in turn, that we have very efficient computations for these systems. So we also wire the neurons differently than they're wired in transformer architecture. So in transformer architectures, there are no loops and there are no convolutions. And in our networks, we support them. And because of these changes, we get some really interesting results. So here's how you can think about it. In most AI models, the models are frozen after training. So this means that they can't improve when they get deployed in the wild. If you want more capability, you have to wait for the next release. Now, because of what's happening inside the liquid neuron, and in particular because of this, our models are still adaptive after training based on the input that they see. And here's an example that shows you how that happens. So this is a video that shows, this is a video, unlabeled video we use to train drones to find things in the woods. And we trained a lot of models to do this task. We trained traditional models and we trained liquid networks. And notice it's summertime. So in the summer, all the models learned how to solve this task using our data. Then we took the models that we trained during the summer and we tried to use them during the fall when the background is very different. So here's what happens with a standard solution. You see the attention map is kind of all over the map, right? And it confuses. So the attention map is much like in the driving example. The robot is confused by the background, doesn't know where to look, and the robot can't solve the task. In the case of liquid networks, the robot is able to find the object and really focus on the task without any distractions from the environment. And so what's interesting is that this solution, trained during the summer, works in the fall, it works in the winter, it works in completely different environments, like from a wooded environment to an urban environment, and from a static environment to a dynamic environment. And so it's really exciting. So these liquid networks get machines to think using this new physics-based model for AI. And because they're small, they can run on smartphones, they can run on robots, they can run on your enterprise computers. They can bring powerful capability without cloud calls. They have some constraints, so they can only work on time series data. Language you can think of as time series because the words in a paragraph or in a sentence come one after the other. Video is a time series data. Financial transactions. There are many sources for time series data. So then we compared liquid networks against transformers, and we saw a lot of exciting improvements. So on physical real world dynamics modeling, we saw 123% improvement as compared to transformers. On information retrieval and text sentiment analysis, we saw 10% improvement. On sequential image processing, we saw 46% improvement. This is because liquid networks are state space models. They are intrinsically able to capture spatio-temporal correlations, which is difficult to capture in a statistics-only model. So encouraged by these results, my students and I started a company called Liquid Networks. And a few months ago, we released some results that show how the performance of our liquid networks compares with existing open source models. And here you can see liquid foundational models, 1B parameters, 3B parameters, 40B parameters. And I should tell you that these models were trained on about 300 GPUs, not the 50,000 GPUs that are currently used in most AI shops. The other thing that's interesting is how the memory usage of liquid networks grows. And so here you can see in purple the memory usage of liquid networks as compared to other state-of-the-art models. And you can see that the memory usage is small. And because of that, we actually don't need so much memory to run them. That's why you can run these models on your phones. So I asked, can we do something better to give more capability to AI models that operate on physical machines? And liquid networks is one example. There are other models and other people who are working on alternative technologies. And this is a very energized and active area of research in AI. The other thing that's really energizing is that once you have multimodal opportunities. So you can do text and you can do video and other models. You can begin to look at abstractions. You can begin to look at text as the basis of increasing the capabilities of our models. So let me give you an example. So in our lab, we combined video and text to get better performance and generalization for liquid models running on cars. And so here's how it works. So let's say you have some images and you have some text describing them. What you can do is you can build a foundational model that aligns the perceptual features of and the language features in the same latent space. And then what you can do is you can train a model to control relative to some concepts. For example, you can train the model to avoid the deer using videos as training data. And then once you've achieved that, then you can say in text, now avoid benches and avoid trees and avoid people and trucks and anything else you want. So this is really cool because at this point, you've learned the capability and you have abstracted it out, and now you can apply it in many different situations. You no longer need video data for each of these different situations. And so here is the system operating in simulation. We have trained in a rural environment during the summer when it's dry during the day to avoid the car. And now we can with zero shot, we can get a generalization to drive in a diverse set of environments, for instance, to avoid the deer, but also to drive in the fall, or to drive at night time, or to drive in the snow, or to drive in rain. And so this is really a kind of a frontier from the point of view of using AI solutions to advance the intelligence of our machines. I also told you that we wanted the AI to not make mistakes. And so now that we have capable AI, we can run this AI on small machines. We can put it on robots. But how do we cope with mistakes? How do we cope with mistakes? Well, we can take the machine learning model that drives a vehicle, and we can wrap it into something we call a barrier function. Essentially, it's a little bit of math that says what safe output is. And with that, we can force the output of our solution into a region that is safe. So you still have a machine learning model. It still computes however it computes. And before outputting the result, we add this layer that essentially forces the result into a safe region. And so it's possible that the core model still makes the mistakes, but the outer layer is kind of like an enforcer to ensure that everything is in order. So we have taken this idea and applied it successfully to several robotic systems. For example, here we have some cars driving with challenging lighting conditions. And here we have another example where we're controlling planes. So this is the Maverick experiment. If you've seen the Top Gun movies, so we call this canyon run, and so we have these canyons. We don't want the robot to crash into the canyon, but we also want the robot to touch some desired waypoints. And in another experiment, we have groups of robots, and these robots are exploring a space. You can see them here in simulation. And here you can see them essentially pushing a box. So I promised you new ways of thinking about AI that build physics in them intrinsically. I promised you something that doesn't make mistakes, and I just showed you how we can begin to develop these kinds of capabilities. I do want to take just a few minutes to talk about the other aspects of physical intelligence, namely the body of the machine and the actual learning. So by now, you likely generated images from text-to-image systems. Who has done that, right? Yeah? All right, so a lot of you have done that. Okay, so we can do text to robot, but not using today's AI solutions because they work on statistics and do not understand physics. And so, for instance, when I asked my favorite chatbot to draw me a new research robot concept that can pick fruit, this is what it came up with. And so it's really wonderful. These designs are so creative, but they have nothing to do with a task that I asked the robot to the system to generate. So I like a lot of these designs. My favorite is this one. And so if we look at this one more carefully, first of all, look at the stem. It's so thin. How can it be possible to lift anything with that stem? And then the other thing that's interesting is that the two sides of the robotic arm are anchored. So how is this going to manipulate or pick anything with anchored arms? And then there are other issues like fabrication and things like that. So in our lab, we developed an AI solution that guides the design process for a new machine by checking and simulating physical requirements. So it's a diffusion process, and you start with a simple language prompt, maybe make me a robot that can walk, and our system can generate the design, the shape, the materials, the actuators, the sensors, the program required to control the machine and the fabrication files to make it. And the process iterates until we get to an optimal design. So this is a blob that walks, but maybe that's not the most optimal. Maybe that's not what we have in the back of our mind when we want a walking robot. Maybe it's something like this. This is an interesting design. It's a table with legs that they're kind of joined together like worms. And eventually, maybe you can even get a walking teapot. So you can do a lot of interesting designs. Here's a case where we wanted a new design for a gripper robot. And here's a case. This is an interesting case. We wanted a very efficient jumping robot. And we started, for that experiment, we started with a 4-bar linkage, which is the state of the art in robotics for jumping. And we actually did our own. We took that initial design, which was done by humans, and we put it through our system to optimize it. And we received a significant increase in the jumping angles. So we went from maybe 0.4 meters. We went to nearly 7 meters. So we almost doubled the way this thing jumped by doing this AI design. So we went from 0.43 meters to 0.69 meters. Which is pretty cool. This is such an optimized design. People have been working on this design for a very long time. Our system made it better. So here you can see the robot again. And we've been also interested. So this is a robot. We wanted the robot to land and stick the landing, kind of like a good gymnast. And so in the case of the human design system, we had one posture, and in this other system, in our system, we actually we were able to stick the landing, whereas the human-designed robot didn't stick the landing. Okay, so we can do text to robot. We can also do image to robot, and so, for instance, this photo can be transformed into a cuddly robotic bunny. And to do that, what we do is we compute a three-dimensional representation of the bunny that then gets sliced and it gets unfolded, and those unfolded layers get printed, and then they get refolded. We attach some motors, we write some code, and eventually we get the bunny you see in this video. And so this approach can be used to generate almost anything from a photo. And so using AI to do text to robot or image to robot is very important because we are drastically reducing the time and resources needing to prototype and test new products. And this allows for a faster innovation cycle. And so now that we can have machines, we can design machines, and we have a basic structure for how they think, we can even have these machines learn, which is the third aspect of intelligence. And so these machines can learn from humans how to do complex tasks. You can think of this as human to robot. And so in our lab, we created a laboratory for kitchen tasks. Now you will see this laboratory this afternoon. We instrument people with sensors, and we collect a lot of data about pose, muscle, even gaze when people perform kitchen tasks. So we need physical data because video alone does not capture the forces and torques required for interactions. And so then we use AI to learn from this data how to get robots to perform those tasks. And the end result is machines that perform the same tasks in a much more human-like way. These are machines that move with grace, and these are machines that also adapt and learn. To me, this is physical intelligence. And so the idea is that now we have a method to teach robots how to do almost anything: food preparation, cleaning, and other tasks. We're still far away from getting the general humanoid robot that can do everything, but we're making progress. And these are some of the nuggets that hopefully will turn into very useful physical assistance for all of us in the future. And so let me stop by observing that the ability to turn photos and words into functional machines, coupled with liquid networks to create powerful brains that can learn from humans, is extraordinarily exciting because it means we can build almost anything we imagine. Transformers and more generally traditional AI has a ceiling. It needs server farms. It has a high energy cost. It makes inexplicable mistakes. But when new ideas enable AI to move into the physical world, we will see incredible breakthroughs and benefits. We will have personal assistants that optimize our routines and anticipate our needs. We will have bespoke machines that help us at work. We will have robots that delight us in our spare time. And so the promise of physical AI is to transcend our human limitations with capabilities that extend our reach, amplify our strength, and refine our precision, and grant us the ability to interact with the world in ways we've only imagined. So physical AI demands a paradigm shift. It requires compact, safe models. And emerging ideas like liquid networks illustrate the potential of physics-based approaches to AI. Now, imagine that in addition to physical innovations, we also have other reasoning innovations, we have design innovations, we have chip innovations, we have fabrication innovation. All of these can come together to create the bespoke machines from our future. Thank you very much.